Precipitation is the product of the condensation of atmospheric water vapor that falls under gravity. The precipitation can be classified as drizzle or light rain, sleet or snow that can partially melt as it falls, snow, graupel or soft hail or snow pellets, and hail or salt precipitation. Also, when a portion of the atmosphere becomes saturated with water vapor, then it condenses and precipitates. Condensation is the process in which water vapor changes into liquid state. Precipitation forms when smaller droplets join together via collision with other raindrops or ice crystals within a cloud. Raindrops range in size from oblate, pancake-like shapes for larger drops to smaller spheres for smaller drops. Unlike raindrops, snowflakes grow in a variety of different shapes and patterns determined by the temperature and humidity characteristics of the air. While snow and ice pellets requires temperatures close to the ground to be near or below freezing. Hail can occur during much warmer temperature systems due to the process of its formation. Before we proceed, if you are new to this channel, please click the subscribe button and hit the notification bell to keep you updated. For specific learning outcomes, at the end of the topic, the student should be able to first, discuss the formation of precipitation, explain the different types of precipitation, expound the rainfall characteristics such as depth, duration, intensity, and height to graph, explain the different types of rain gauges, perform computation using estimation of missing rainfall data, and solve problems using aerial rainfall method. So first, let's define the term coalescence and Bergeron process. So coalescence occurs when water droplets fuse to create larger water droplets, or when the water droplets freeze into an ice crystal. That's what we call Bergeron process. For formation of precipitation, first we have drizzle, precipitation in the form of fine sprinkle of very small drops smaller than 0.5 mm. Then rain, precipitation occurs in the form of large water drops with a diameter larger than 0.5 mm. Smaller drops are called cloud droplets, and their shape is spherical. As a raindrop increases in size, its shape becomes more oblate, with its largest cross-section facing the incoming airflow. Rain can be classified as light, moderate, or heavy, but not in size but in terms of intensity. Light rain has an intensity of 0.5 mm per hour. Moderate rain has an intensity of 0.5 and 4 mm per hour. And heavy rain is more than 4 mm per hour. Ice pellets or sleets, a form of precipitation consisting of small translucent balls of ice, usually smaller than hailstone. Hail forms in storm clouds when supercooled water droplets freeze on contact with condensation nuclei such as dust or dirt. The storm's updraft blows the hailstones to the upper part of the cloud. Hail has a diameter of 5 mm or more. Stones just larger than golf ball size are one of the most frequent reported hailstones. Hailstones can grow up to 15 centimeters or 6 inches and weigh more than 500 grams. Snowflakes are snow crystals formed when tiny supercooled cloud droplets freeze. That's about 10 micrometer in diameter. Once a droplet has frozen, it grows in supersaturated environment. Because water droplets are more numerous than the ice crystals are able to grow to hundreds of micrometers or millimeters in size at the expense of the water droplets. Glaze. It is a precipitation that falls as rain and freeze when striking the ground. It occurs when cold layer of air with a temperature below 0 degrees Celsius, when objects such as trees and power lines on which the precipitation occurs are very cold. Glaze occurs on them, also known as freezing rain. Diamond dust. It is also known as ice needles or ice crystals, forms at temperatures approaching -40 degrees Celsius due to air with slightly higher moisture from aloft mixing with colder surface-based air. They are made of simple ice crystals that are hexagonal in shape. Dew. It is form of precipitation which does not occur because of condensation in higher layer of atmosphere, but it is formed by condensation directly on the ground. It occurs at night when the ground surface is cooled by outgoing radiation. Under rainfall characteristics, we have depth, duration, rainfall intensity, and height to graph. For depth, rainfall is measured as length. The unit is millimeter. It is the depth to which water would accumulate if all the rainwater remained at the same place where it fell without flowing off or seeping into the ground. This has to do with how much water has fallen over a period of time. Duration. It is defined as the period of time during the continuous rain is observed at a given point at a given area. It is expressed in hour. Rainfall intensity refers to the ratio between the total amount of rain during a given period and the duration of the period. Rainfall intensity is expressed in depth units per unit of time, or that's millimeter per hour. Height to graph is a graphical representation of the distribution of rainfall intensity over time. For our measurement, there are two types of rain gauges for measurement of precipitation. First, non-recording rain gauges, and second, we have recording rain gauges. Non-recording rain gauges are commonly used. They do not record the data and collect only rain, and this collected rain is then measured in a graduated cylinder. The standard gauge of US Weather Bureau has a collector of 200mm diameter and 600mm height. Rain passes from a collector into a cylindrical measuring tube inside the overflow can. The measuring tube has a cross-sectional area of 1/10 of the collector, so that 2.5mm rain will fill the tube to 25mm depth. A measuring stick is marked in such a way that 1/10 of the centimeter depth can be measured. In this way, a net rainfall can be measured to the nearest 1mm. Recording gauges are those which automatically record rainfall without any bottle reading. The worker is not required to record the reading, but instead mechanical arrangements are there by which total rainfall is recorded automatically on graph paper. A graph of total rainfall versus time, which known as mass curve of rainfall, is plotted by the gauges. Weighing precipitation gauge. A weighing type precipitation gauge consists of a storage bin, which is weighed to record the mass. Certain models measure the mass using a pen and rotating drum, or by using a vibrating wire attached to a data logger. The advantages of this type of gauge over tipping buckets are that it does not underestimate intense rain. It can measure other forms of precipitation, including rain, hail, and snow. These gauges are, however, more expensive and require more maintenance than tipping bucket gauges. The tipping bucket rain gauge consists of a funnel that channels the precipitation into a small seesaw-like container. After a preset amount of precipitation falls, the lever tips, dumping the collected water and sending an electrical signal. Optical rain gauge. These have a row of collection funnels. In an enclosed space between each is a laser diode and a phototransistor detector. When enough water is collected to make a single drop, it drops from the bottom, falling into the laser beam path. The sensor is set at right angles to the laser so that enough light is scattered to be detected as a sudden flash of light. The flashes from the photo detectors are then read and transmitted or recorded. Satellite estimates. Although surface precipitation gauges are considered the standard for measuring precipitation, there are many areas in which their use is not feasible. This includes the vast expanses of ocean and remote land areas. In other cases, social, technical, or administrative issues prevent the dissemination of gauge observations. As a result, a modern global record of precipitation largely depends on satellite observations. So let's proceed to optimum number of rain gauges. If there are a number of rain gauges already installed in the region, the information from these gauges can be used to determine the optimum number of rain gauges required for the area. The optimum number depends upon the coefficient of variation of the mean rainfall values at existing stations and the allowable degree of error. For our formula, we have optimum number of rain gauges, M, is equal to CV over E raised to the second power, where CV is the coefficient of variation, sigma is the standard deviation, P bar is average annual rainfall, where N is the number of existing rain gauges and P is the mean annual rainfall. The additional rain gauges will be M minus N, which will be properly distributed over the area. So let's try sample problem number 1. Calculate the optimum number and additional rain gauges in a catchment area from the following data. We have number of existing rain gauges, 8. Mean annual rainfall at the gauges in millimeter, 1,000, 950, 900, 850, 800, 700, 600, and 400 millimeters. The permissible error is 6%. Let's create a table. First, we have the column for the mean annual rainfall. Next column is number of rain gauges. The third column is the permissible error. Then the average annual rainfall. The fifth column is the summation of P minus P bar squared. Then we have the column for standard deviation. Compute for the value of standard deviation. Then substitute the value of standard deviation to the formula of coefficient of variation. Then substitute the value of coefficient of variation to the formula of M. Then we have the optimum number of rain gauges and the additional rain gauges. Now the additional is M minus N. So 19 minus 8, the result is 11. Estimation of missing rainfall data. Before analyzing the rainfall data of a region, it is necessary to check its continuity. The data is discontinuous when a particular rain gauge is not operative for some period of record. It becomes necessary to supplement the missing data by an intelligent estimation of the missing data. It's usually estimated from the variable data of neighboring rain gauge stations called index stations. The normal annual rainfall is the average value of the annual rainfall over a specified period of 30 years or so and updated for every 10 years. The daily rainfall collected from the rain gauge stations is total to obtain the yearly rainfall of the year. The mean annual rainfall is equal to the average of the total yearly rainfalls of several consecutive years and also known as average annual rainfall. The missing mean annual rainfall of station X is P sub X. So there are two methods in solving the missing mean annual rainfall. So we have the arithmetic mean method and the normal ratio method. For arithmetic mean method, when the mean annual rainfall at each of the index stations A, B, C is within 10% of the mean annual rainfall of station X, a simple average of the values of the index station is taken. So the formula is Px is equal to 1/3 of Pa plus Pb plus Pc. Next, we have normal ratio method. When the mean annual rainfall at each of the index stations differs from the station X by more than 10%, the normal method is used. And here's the formula for normal ratio method. Let's try sample problem number 2. For aerial precipitation estimation, the rainfall recorded by rain gauge represent the rainfall at the station and is also called point rainfall. The determination of the average precipitation over an area, a large number of rain gauges are installed and can be determined using these three methods. First, arithmetic mean method, second, Thiassen method, and third, isohyetal method. For arithmetic mean method, the average depth of rainfall over an area is taken as the arithmetic mean of the rainfall depths of all the stations within the catchment area. For arithmetic mean method, the average depth of rainfall over an area is taken as the arithmetic mean of the rainfall depths over all the stations within the catchment area. Thus, the formula is For Thiassen Polygon Method, the positions of the rain gauge stations are marked on the plan of the catchment area over which the average rainfall depth is required. The adjacent rain gauge stations are then connected by straight lines. Thus, the entire area is divided by a series of triangles. The rain gauge outside the catchment area but the neighborhood should also be considered. Perpendicular bisectors are drawn on the connecting lines to form polygons around stations. Each polygon contains only one rain gauge station. For the determination of the average depth of rainfall, a boundary of the catchment is taken as the outer limit of the Thiassen polygons, and the areas of the polygon are determined by the planimeter by overlay grid. A planimeter, also known as platometer, is a measuring instrument used to determine the area of two-dimensional shape. And then here's the formula in computing the total aerial rainfall using Thiassen method. For isohyetal method, potentially most accurate approach but subjective. First, plot gauge location on the map. Subjectively, interpolate between rain amounts between gauges at a selected interval. Connect points of equal rain depth to produce lines of equal rainfall amounts, or that's what called isohyetes, and compute for aerial rain using the formula. Isohyetes are the contours of equal rainfall depth. For plotting an isohyetal map, rain gauge stations are marked on the plan of the catchment. The rain gauge stations located outside the catchment, but it is a neighborhood also marked. The isohyetes of various rainfall depths are then drawn by interpolating the values of the rainfall. A linear variation of rainfall depth is assumed between the two rain gauge stations. Okay, let's try sample problem number 3. For a given observed precipitation points A, B, C, D, E, F, G, and H and I are as follows. Calculate the average precipitation precipitation for the shaded area under observation. Use arithmetic mean area method. The area is 4,410 square kilometers. Compute the average of precipitation of stations C, D, E, F, and G only. However, stations A, B, H, and I are not included in the computation because these stations lie outside the catchment area. So to calculate the average precipitation, we will sum up stations C, D, E, F, G, then divide it by total number of rain gauges, 5. So the result is 47.96 millimeters. Let's try sample problem number 4. Calculate the average rainfall over the catchment shown in the figure by the isoheital map method. So we're given the isoheights and areas. So we're given isoheight, area, and precipitation. All we have to do is multiply the amount of precipitation by the area. Then compute for the summation of precipitation and the area. Proceed with the formula. The result is 53.105 millimeters. Let's try sample problem number 5. A small urban watershed has 4 rainfall gauges as located in the figure. The total rainfall recorded at each gauge during a storm event is listed. Compute for the mean areal rainfall for the storm using TSN Polygon Method. For the amount of precipitation for station A, we have 80.2 millimeters. Precipitation for station B, 72.8 millimeters. Amount of precipitation for station C, 74.2 millimeters. And the amount of precipitation for station D is 78.5 millimeters. So first, solve for the area of station A. The area is triangle. Then solve for the area of station B. The area is trapezoid. Solve for the area of station C. The area is trapezoid, same as area of station B. And lastly, solve for the area of station D. That's area of 2 triangles. After computing the area for each station, multiply it by the amount of precipitation. Then compute for the summation of amount of precipitation multiplied by the area. And then proceed with the formula. The result is 75.28 millimeters. The hyetograph and the cumulative mass curve. Rainfall gauges may be of recording or non-recording type, but recording gauges are required if the time distribution of rainfall is desired, as is often the case for urban drainage or flooding control works. Point rainfall can be plotted as a cumulated total rainfall or as a rainfall intensity at a particular gauge. The first plot of rainfall over time is referred to as cumulative mass curve. The second plot is hyetograph, which refers to the plot of graphical representation of the distribution of rainfall or rainfall intensity in millimeters per hour, or that is inches per hour over time in hour. Rainfall intensity is equal to present reading minus the previous reading divided by the time interval, that is I equals R sub 2 minus R sub 1 all over time. In a record of precipitation from recording gauge for a storm in Panay Island for the period between midnight and 11:15 a.m. On the same day, for a given data, develop a rainfall intensity from 5:45 to 11:15 a.m. Hyetograph and mass curve also determine the maximum intensity rainfall. Then graph the computed values. What is the value of maximum intensity rainfall? That will be all. Thanks for watching. Hanggang sa muli. Paalam!